Hello again, my name is Janeline Macy Lola and welcome to my another integral calculus video tutorial. Our first topic is area computation. We have area equals to the integral between a to b f of x dx. This is applicable for finding an area between the interval a to b bounded to its curve and x-axis. Of course, there are also other variants. It depends on the problem. Let's try to understand more clearly. To analyze, we will have to take vertical strips where we have a very small width of a strip used to approximate the area. As you can see, we have formed like a rectangle strips. To get the area, we have to find the interval under the curves. We have a to b. From right to left, we have our lower limit a and higher limit b. By applying the rectangle formula, we have our height y high minus y low, and our base is dx. You can also take the horizontal strips to find an area where the height is your dy and your base would be x right minus x left. Also, watch out to find the interval since our dy depends on how far vertically. Let's proceed to solve a problem. Find the area of the region bounded by y minus 2x squared equal 10 and y minus 16 equals to 4x. First, let's equate two functions to find the intersection. We write these given functions to separate its y. Then we can input its equivalent. We have obtained the value of x. To get its value of y, use the given function to input the value of x. There we have obtained the value of y. We can now plot the points of intersection. We know that the function of this line is the given linear equation. We also have a given quadratic equation, then it is a parabola like this curve. If you don't know how, try to input the value of x between -1 to 3 using the given quadratic equation. Let's try solve for area. How about we take the sample of vertical strip? The higher y is the linear function, which is the y's of 2, and the lower y is the y's of 1, with a base dx. To find the interval, we know dx depends on how far horizontally. Between points of intersection, we have -1 as lower limit and upper limit is 3. The area of the strip is the quantity y's of 2 minus y's of 1 times dx. Input the values equivalent in terms of x. We can now substitute, integrate, and simplify. This is the final answer. Next, our second topic, centroids, referred to as the balance point of the area. These general formulas is used to find the centroid, the balance point of a planar area under a curve. Let's understand first about Varignon's theorem. This states that the moment of a force or an area about a point is equal to the sum of the moment of its components about the same point. For example, first, let's find the area of its components. Let's add up all area components and we have the area total of 13 squared units. And then we can apply the Varignon's theorem. We know that the centroid of the area 1 along the x-axis is 1.5 to the right. As for the area 2, divide the side by 2 and we got 3 plus 1, 4. We can now compute the x value of the centroid. Correction, it should be 2.27 units, not unit. Unless we can say 1 unit. Also, it should be the area is units squared. Sorry for my mistakes. Now let's find the y value of the centroid. The centroid of area 1 located at 1.5 high. And the area 2, the centroid is located at 1 high from the x-axis. Now compute for y bar. Then the centroid of this whole area is located at point 2.27 and 1.35. But how about to find a centroid of an area bounded by curves? Then we use the integration using the Varignon's theorem. This integration is what we call principle of moments, also called as the first moment of the area, where we get a sample of a very small element of an area bounded by these curves or lines. Let's try to solve a problem using the principle of moments. First, let's find the points of intersection by equating the two given functions. If x raised to 5 halves equal to 1, then our x must be equal to 1. Use either of the given function to input the x equals 1 to find the y value. We can plot our points of intersection. We also have the intersection at the origin, since if we input the 0 value of either of the two given functions, the other value is also equal to 0. To plot the curves of the given functions, we try to input value of a variable between the points of intersection. We now know the given function y equals to square root of x is the upper curve, and the lower curve is the function y is equal to x cubed. Now we have an area bounded by these curves. We can now use integration to find the area. I'll be using a sample of a vertical strip. Then it's the quantity y high minus y low times dx. Then the limit starts from 0 to 1. since dx depends on how far horizontally. Input the value in terms of x and integrate and solve. The area total is 5/12 square units. Now we can apply the principle of moments. We know our dA is equal to quantity square root of x minus x cubed times dx. Input and solve for x bar by simplifying and integration. Again, to solve for y bar. Notice we cannot integrate with y, so we have to find the value of y. We have a point xy on the centroid of the strip. From the strip, the y centroid is located at a half of y high plus y low. It means that our y must be half the quantity of square root of x minus x cubed. Input the y and solve for y bar. The value of y bar is 0.43 units. Then the centroid of the area bounded is located at a point of 0.48 and 0.43. Third topic, we have the volumes, the solids of revolution. We have the three general formulas. 1. The disk method, solid with no hole. Washer method, solid with a hole. And shell method, rotating around y-axis or vertical lines. Let's proceed to solve a problem. Find the volume of the solid obtained by rotating the region by y equals to cube root of x and y equals to x/4 about y-axis. Rewrite the given functions to separate the x that might be helpful in the future. Let's equate the two given functions to find the point of intersection of the region. We have obtained a point 8 and 2. Plot the points of intersection. We have 8, 2 and a point at the origin. We already know the function of a line, which is that, and to find the curve of the other function, we'll input 4. Then the curve must be like this. By taking a horizontal strip and rotate around the y-axis, we have formed a hollow circle on its top view. Then we can apply this by washer method. You can also use the shell method. It depends on you. We let the big R from the outer edge and the small r from the inner edge. From taking horizontal strips, our limit interval will be from 0 to 2. Our big R of y is the given linear function y equals to x/4, since it's the bigger circle, and the other given function is the smaller circle. Then we can input in terms of y. Solve, integrate, and simplify. This is the final answer. Fourth topic, length of a curve. These general formulas are used to calculate the arc length of a curve between limits or from one point to another. Again, from interval a to b, we can find the length of a function or a curve by using this formula. Let's try to solve a problem right away. Find the length of y equals to x squared from x minus 2 to x equals to 1. First, compute for the derivative of y. We have 2x. And get the square of 2x, we have 4x squared. Then we can apply the formula to find the length. Correction, this is x equals to negative 2. Then our lower limit will be negative 2 to 1. Then input the values. Compute and integrate, we have our length 6.13 units. From here, negative 2 to 1, this is our arc length. Simple, right? Fifth topic, area moment of inertia. This is to measure how an area resists bending or rotation about an axis. This is applicable when the shape and the axis of rotation are known. Also, the unit used for an area moment of inertia is raised to the fourth power. Let's proceed to solve a problem. Find the moment of inertia of the area bounded by x squared equals to y equals to 9, and y-axis. Calculate with respect to x-axis and y-axis. Let's try to calculate first about the moment of inertia with respect to x-axis. To analyze, let's graph the given functions, where we have parabola and lines forming an area. Then we have the dA from taking a horizontal strip. Then it is a quantity of x right minus x left times dy. Then input in terms of y. Our x right is the parabola function, which is equivalent to square root of y. And our x left is the y-axis, so it means it is 0. Simply, our dA is the square root of y dy. Now we can apply the formula to find the moment of inertia with respect to x-axis. Same also about the process to find the moment of inertia with respect to y-axis. But we are taking a vertical strips. Then our dA must be the quantity y high minus y low times dx. Input in terms of x, our higher y is 9 and our lower y is the function parabola, which is x squared. Now, we can input the formula of moment of inertia with respect to y-axis. Watch out to input limits since dx depends on how far horizontally. Finally, to our last topic, work, about pumping of water. This formula is used when the liquid is being lifted from a tank, like pumping water out. The interval from A to B represents only the vertical limits of the liquid in the tank. Also, account for changing area if needed, like if it's a cone or a paraboloid tanks or etc. Proceed to solve a problem. A conical tank is 5 meters tall with a radius of 1 meter. It's filled with water up to 2.5 meters. Water is pumped out through vertex to an outlet 3 meters above the water level. Find the work done. This is what it looks like to draw an illustration. To solve for work, first let's find the x value through ratio proportion before we solve for a of y. We know from the given we have the radius of 1 meter. And also we have a conical height 5 meters tall. Then we can use the ratio proportion. Now we can solve for a of y equals to pi x squared, since we get a differential circles inside the conical tank. As for d of y, this is the vertical distance where the differential slices must be lifted. So we first find the total distance starting from the bottom to the outlet. From the illustration, we have 3 meters plus 2.5 meters. Minus by y, since y is the unknown and the varying value that each time the differential slices that must be lifted. Then our d of y is 5.5 minus y. We can now solve for work. The limit interval focuses on a liquid being lifted, then it must be the lower limit is 0 to 2.5 water level. The density of the water is 1000 kg per cubic meter, and the gravity is 9.81 meter per second squared. Input all the required values, then integrate. The work done is equal to 23,274 joules. Thank you for watching.